just go over some fun research that I've been looking into for quite some time, which is nuclear well control, actually. If I could figure out how to get a background on this thing, I would do that. But I guess I want to start with what would you do in the event you had a well control event where you have essentially a jet of flame shooting up 120 meters into the sky that's been burning for 3 years, and you haven't been able to put it out with any conventional well control method that is available. What are the technical options remaining? And would you be willing to consider using a nuclear bomb in order to do a well kill? Is it a reasonable engineering solution? So for those of you that don't know, my name is Jonathan Paulette. I'm a oil and gas professional with 25 years of experience in the industry, 15 of that spent working overseas across 11 different countries. So this is Practical Energy Insights, and it's a channel focused on bringing complex and historically significant topics into the energy sector to energy professionals around the world. So today, I want to open the discussion on program number 7, which was the Soviet Union's ambitious initiative to use peaceful nuclear explosions, or P&Es, for industrial development. In this first part of the series, we're going to do a deep technical dive into the event that started it all, which is the Erdőbulak blowout in the Soviet Union. So, our story begins with well number 11 on December 1st, 1963, at the Erdőbulak gas field in southern Uzbekistan. Geologically, the Erdőbulak field is a complex combination structure within the Amudarya Basin, and the reservoir is characterized by massive terragenous sediment layers, primarily from the Jurassic and Cretaceous periods. So gas is sequestered between an anhydrite layer and limestone at depths exceeding 2,400 meters. The crew was drilling well number 11 using early generation Uralmash rigs, the workhorses of the Soviet oil and gas industry. They hit an abnormally high pressure gas horizon at a depth of 2,409 meters. From a technical well control perspective, this was the perfect storm. The reservoir pressure was recorded at over 300 atmospheres. For whatever reason, we use different units around the world. Sometimes you use bars, sometimes it's atmospheres, sometimes it's PSI, but 300 atmospheres would be around 4,400 PSI. And it was saturated with high concentrations of hydrogen sulfide, which is H2S, a highly toxic gas that can kill you with very, very low concentrations. So we have to look at why this escalated. In the early 1960s, Soviet drilling standards were still evolving. The wellhead at well number 11 was not equipped with a modern blowout preventer, or BOP stack, and the steel used for the casing and wellhead was standard grade, not rated for sour service. Any specialist will know H2S is a silent killer for metal. It initiates rapid sulfide stress cracking in the wellhead, and the structure mechanically failed. The wellhead ejected from the wellbore, and the gas ignited. For the next 1,064 days, nearly 3 years, the well burned with a flame reaching 120 meters in height. It was consuming an estimated 12 million cubic meters of gas every single day. The head of the task force described the scene in his journals as scorched earth, where migratory birds were consumed by the thermal radiation of the flame before they even touched the ground. Before the nuclear option was even whispered, the Soviets threw everything conventional that they could possibly think of in terms of well control. They used water cannons, high volume chemical suppressants, but the sheer momentum of the gas flow made it impossible to establish a stable hydrostatic column. They brought in heavy bulldozers to build a protective sand berm around the torch, 120-meter high torch, to restrain its thermal impact on the surrounding area. They even deployed field artillery, like military artillery, to shoot the debris of the melted rig clear, hoping to attempt a surface cap. Diversion attempts were made to bleed off pressure into nearby wells, but the H2S corroded the diversion equipment almost as fast as it could be installed. The core problem was the unknown condition of the lower 1,000 meters of the wellbore, which had not been logged fully or cemented. Gas began migrating into unintended horizons, creating a secondary griffins or surface seeps. By 1966, the ground around the site was so hot that communication between engineers was only possible through hand signals. Couldn't even use radios. So, the nuclear operational plan for well control. In the summer of 1966, the Soviet government authorized Design Bureau number 11 at Sarov to proceed with a nuclear seal. This was the first time this had ever been attempted. This wasn't a surface blast. It was a surgical subsurface intervention. The plan involved drilling 2 slanted or deviated emplacement wells towards the runaway wellbore. Using early turbo drill technology and rudimentary directional surveying, one well successfully navigated to within 35 meters of the target wellbore at a depth of 1,532 meters. It's pretty remarkable when you think about it. This is 1966, and they were able to directionally drill to within 35 meters of the target wellbore. This specific depth was chosen because the host rock was a thick plastic clay formation. In geomechanics, clay is ideal for sealing because it undergoes significant compaction under a shock wave without creating extensive radial fractures that could provide new pathways for gas to escape. On September 30th, 1966, with approval from High Command, a 30-kiloton nuclear device, roughly twice the yield of the Hiroshima bomb, was lowered into the slant well. The hole was stemmed with cement to prevent atmospheric venting. They pulled the trigger, and technical observers reported that for 22 to 30 seconds after the underground tremor, the flame flickered and then died out completely. So the jet-like 120-meter high roar of this late 2025 and 2026, the Uzbekneft, I'm going to butcher this name, but Uzbekneftgaz reports that the Amudarya Basin remains central to the Uzbekistan's energy strategy, with production maintained through modern enhancement techniques and new wells. The success of Erdubulak gave Soviet scientists enormous confidence, but the geology of the next target would be twice as challenging. So this isn't the only time that they actually tried a nuclear well control. This was the first time they tried it, and it was successful. So they kind of felt, oh, well, this is a good option. But some of the future events some were successful, some were initially successful, but then failed ultimately because the type of rock that they had to use was different. They didn't have the clays, and they couldn't get the same kind of result to fuse the wellbore shut. So the geology of the next target would be twice as challenging. What happens when the pressure is 8,500 psi and the host rock is a massive salt dome? In part 2, I'm going to go live again in a few days. We'll analyze the high pressure intervention at Pamuk and the catastrophic failures of Fakkel and Pyrite. And you won't want to miss why one nuclear blast resulted in a mushroom cloud and an ongoing Arctic disaster. So if you found this technical breakdown interesting, please hit that like and subscribe button, and subscribe to Practical Energy Insights, and leave a comment based on the technology of 1966. Was the nuclear option for well control at Erdubulak a stroke of genius or a desperate gamble? Was it scientifically significant? I think there was a lot of learnings from it. We obviously don't do this today, and I believe the Soviets were the only ones to attempt it. So very interesting. There's other uses for the peonies or peaceful nuclear explosions in terms of mining and some other applications as well. So make sure you watch out for that. I'll go live in a few days and cover those topics. All right. Appreciate your time. Thanks for tuning in. And I've got to get to work. So hope you guys have a good day. Stay safe. And thanks for watching.